In this problem, we're looking to find the total moment around point O caused by these two forces F1 and F2. So we need to find the moment around point O. And we're in 3 dimensions here, so that moment around the point O is going to be a vector quantity. It's going to have I, j, k components. And we're given, well, really all the information we need is in the diagram, so there's nothing extra really given in this problem for us. All right, so it's not an equilibrium problem. We don't need a free body diagram, but our own diagram is going to be useful here, even though it's really just going to replicate more or less the one that we are provided. So I'm going to stick with the given coordinate system, just so that everything is going to be easier when I translate it. So I have the origin down here. That's where I want to know the moment about. And I have this pipe happening. And even though here they call point A the bottom, I'm going to say that this, where the force is being applied as point A, will be a little bit easier for us. And then point B, where force 1 is being applied. Right, so here we have F1. I won't copy down its Cartesian component form because it's already provided. We're going to use that when we take the moment equation. And over here we have F2. So really all I want is to put in the coordinates I'm going to need. So how do I go A? From the origin, I'm going to go 1 in the positive z and 2 in the positive y and nowhere in the x direction. So that's going to be 0, positive 2, positive 1 meters. And B, I'm going to go 1 in the z, 2 in the y, and then negative 1.5 in the x. So negative 1.5 to 1 meters. And I guess just for completeness, I will put in this information here, 300I, 150J, and 200K. And that's in newtons, and F2 is negative 450K newtons. That way our diagram does have all the information we need, even though, again, it looks a lot like the one we were provided. Okay, so equation-wise, again, no equilibrium equations in this one. We're not in equilibrium. But we do need to realize that if we want to find the moment around point O, it's going to be the sum of all the things that cause moments around that point. So we have F1, which is going to be a force a distance away through O. It doesn't act through O, so it will cause a moment. And F2 does not have its line of action pass through O, so it will cause a moment around point O. Now, let's look at F1 first. So it's going to be an R cross an F1. These are vectors. We need Cartesian coordinates here. And now the R I need to use is going to go from O. Give myself a little bit more space here. It always will start at the point I want to know the moment about to any point on the line of action of, in this case, F1. So based on the coordinate I put in, F1 acts through B, so I'm just going to use B as the end coordinate for this position vector. Again, it could be any point that F1 passes through or its line of action passes through. The only one we have easy access to is B. Right, so R cross F, specifically ROB cross F1, I'm talking about first. Again, I just want to point out here this O and this O match, this B as a point that F1 passes through. Right, so the green line is just for emphasis here. Right, and then I will add to that the moment caused by F2. So R cross F2. Again, it will start at O because that's the point I need to know the moment about, and then it will end at any point that F2 passes through or its line of action passes through. So I did here put A as a value or as a point that F2 passes through. So that's why I'm going to use ROA here. We actually could have in this one used a different point. For example, this original placement of A would have been okay also to use because we know that F2 also passes through point A or its line of action passes through point A. Either one would be okay. I'm going to use the A as I put in my diagram though, the point on the actual bar where it emanates from. But either would be fine to use. And again, just for the emphasis here, this O and this O match. This A is a point that F2 passes through. So we have two cross products that we need to contend with here. So I'll give ourselves some extra room here. So MO is going to be, let's do the first cross product. We have I, J, and K as the first row. And then the second row is going to be the components of ROB, which is going to be point B minus point O. Well, O is the origin, so that's easy enough that we know ROB is going to point from O to B. I'll at least illustrate it here. That's ROB. And then this is ROA. So ROB is B minus O. We have a negative 1.5, a 2, and a 1. I like to put in here the units so that we remember them. And then it's R cross F1. So now the components of F1, negative 300, positive 150, positive 200, and that was in newtons. And our second cross product, IJK at the top. Now ROA is A minus O will be 0, 2, 1 meters. And F2's components 0I, 0J. And negative 450 in the K direction, that's in newtons. We have two 3x3 determinants, so I'm going to use the cofactor expansion to go through these. So I'm going to start with this first one. I want the cofactor in front of I. So I want everything in this matrix that's not in the same row or column as I. So J and K are eliminated, they're in the same row. The negative 1.5 and negative 300, so I'm left with 2, 1, 150, and 200. Minus, I'm still on this first matrix, so the J cofactor is always subtracted. So I'm left with 1.5 and 1, negative 300 and 200. And then the K cofactor. Negative 1.5 and 2, negative 300 and 150. So all three of these were just an expansion of the first determinant. I still will have three more terms from the second determinant. So the I cofactor, this comes from the second. I'm left with 2, 1, 0, negative 450. Minus, J is always subtracted. I have 0, 1, 0, negative 450. And then the K cofactor. I'm left with 0, 2, 0, and 0. And these are the expanded from the second determinant. So I have a bunch of terms here. I have a bunch of 2x2 determinants, but now these I know how to deal with one at a time. So this 2x2 determinant here is going to be 2 times 200 minus 150. So again, what do we do? It's going to be the product of the main diagonal minus the product of the off diagonal. So 2 times 200 minus 150. That is 400 minus 150. We are left with a positive 250, and that will be times I. Now our J term, so this negative comes down, and now on the inside, we will have negative 1.5 times 200. That is going to be minus 300. And we're going to subtract 1 times negative 300 is also negative 300. So we have negative 300 minus negative 300 will actually leave us with 0. So with these determinants, we want to be very careful on the sign that is coming off of them, because there's a lot of negatives that are going to be floating around here. So we end up with 0 in the J. And finally the K, we have negative 1.5 times 150 minus 2 times negative 300 is going to result in a positive 375. Okay, because we're going to be subtracting negative 600 on the off diagonal, which will add 300. Now for the second grouping, we have 2 times negative 450 minus, well, 0. Be a negative 900 minus our j term. We have 0 times negative 450 is 0, minus 0, this will leave us with 0, plus, and our k term also 0 minus 0 leaves us with 0. So we've expanded all 6 of our cofactors, and now we are ready to combine our like terms. We have here a positive 250i and a negative 900i, so we can group all of that together into a negative 650i. We have a 0j, I forgot the j over here, and another 0j, so we actually have no j in our final term. And our k's, we have a 375k and a 0k is just going to give us 375k. And now we're doing a cross product, so the units will get multiplied. So that's why I put them here to remind us what units we were working with. Will be in Newton meters. So typically it's going to be force times distance is how we're going to express our unit in the end. So the total moment around point O, we have this vector quantity, negative 650i plus 0j plus 375k Newton meters.